Welcome to the I²C Interface course of the HT8 MCU Basic Tutorial. This course will introduce the I²C interface of the HT8 MCUs from 7 sections, which are I²C Interface Introduction, I²C Communication Mode, Relevant Registers, I²C Interface Operating Principle, SIM-independent interrupt, application examples, and considerations. I²C Interface Introduction. What is an I²C interface? The I²C interface is a synchronous, half-duplex, serial data transmitter, and operates as a master-slave type, which is usually used to connect multiple sensors for data sampling and transmission, such as temperature and humidity sensors, EEPROM memory, etc. The I²C interface uses 2 lines for communication. One is the serial clock line SCL used for clock signal transmission. The clock signal can only be generated by the master and transmitted to the slave, which is unidirectional. The other one is data line SDA used for data transmission. Both master and slave devices can transmit or receive data through the SDA line. For more details, please refer to the application note, HT8 MCU I²C Interface Application Guidelines and Example, on Holtec's official website. Synchronous means the clock signals of the transmitter and the receiver must be the same, with the master providing the clock to the slave. Half-duplex means to allow only one direction data transfer at a time. And serial means to use one data line to transmit data bit by bit in sequence. I²C Communication Mode. So how is the data transmitted? Firstly, the SCL line of the I²C communication is used for clock signal transmission, which is generated by the master. The SDA line is used for data transmission. The data transmission requires 4 steps. A start signal, a slave address transmission with a read-write bit, a data transmission, and finally a stop signal. Let's go through these steps one by one. All communications on the I²C bus is initiated with a start signal, which is generated by the master on the bus. The start signal refers to that the master on the I²C bus controls the SDA line to change from high to low when the SCL line is high. If the master wants to communicate with a slave device, but all slave devices are on the same bus, how can the master accurately complete the communication? This involves the slave address. The slave devices on the bus each has a unique 7-bit slave address. After transmitting the start signal, the master will transmit a frame through 8 clocks, which contains 7 slave address bits and 1 read-write bit. All slave devices on the bus will receive this data and compare the 7-bit address with their on-slave address. Only the slave device which matches the address will pull low the SDA line on the 9th clock to acknowledge the master. Other slave devices will not acknowledge and therefore ignore the subsequent data. In this way, the communication between the master and the specific slave is implemented. Then what is the purpose of the read-write bit? This bit determines whether the master wants to transmit data or receive data the next step. After the master has transmitted the address and been acknowledged by the corresponding slave on the bus, according to the aforementioned read-write bit meaning, the next step should be the master or slave to transmit data. After the transmitter completes the data transmission through 8 clock cycles, the receiver will transmit an acknowledge signal on the 9th clock cycle. A high level means not to acknowledge and the receiver no longer receives data. A low level means to acknowledge and the receiver will continue to receive data. As shown in the figure, the signal on the 9th clock of data transmission is a high level. It means to not acknowledge and the receiver no longer receives data. When the master receives a not acknowledged signal after data transmission, or when the master has received enough data and transmits a not acknowledged signal to the slave, the master then transmits a stop signal to terminate the I²C communication. The stop signal refers to that the master on the I²C bus controls the SDA line to change from low to high when the SEL line is high. Introduction to relevant registers. First, let's look at the SIMC0 register. The SIM2, SIM1 and SIM0 bits are used to configure the SIM operating mode, including the SPI master mode and master clock frequency, SPI slave mode, and I²C slave mode. Note that the I²C interface of the HT8 MCU can only be used in slave mode, while the master mode requires a software emulation. The SIMDEB1 and SIMDEB0 bits are used to select the I²C debounce time. The SIMEN bit is the SIM enable or disable control bit. The SIMICF bit only takes effect in SPI slave mode, which will be introduced in the SPI interface course. The SIMC1 is the I²C Interface Status Register. The HCF bit is the I²C Bus Data Transmission Complete flag, which is read-only. The HAS bit is the Address Match flag and is read-only. The HBB bit is the Bus Busy flag and is read-only. The HTX bit supports read and write, and is the Slave Operation Mode bit. The TXAK bit supports read and write. It is the I²C Bus Transmit Acknowledge flag, which is transmitted to the bus after the receiver has received 8 data bits. This flag should be cleared before further data is received. The SRW bit supports read and write. It is the Slave Read-Write flag. The IAMWU bit is the Address Match Wake-Up Control bit, which supports read and write. If this bit is set to 1, when an I²C address match occurs, the system can be woken up from the sleep or idle mode, then this bit must be cleared to ensure correct MCU operation. The RXAK bit is the Bus Receive Acknowledge flag, which is read-only. The SIMA register supports read and write. Its higher 7 bits store the slave address. The lowest bit is undefined. If the address transmitted from the I²C master matches the slave address, the communication between the two devices will start. The SIMD register is used to store the transmitted or received data. The SIMTOC is the timeout control register, which supports read and write. The SIMTOEN bit is the timeout enable bit. The SIMTOF is the timeout flag. It is set high when a timeout occurs and can only be cleared by software. The SIMTOS 5 to 0 are timeout period setting bits. The clock source for timeout control is divided by 32, and the timeout formula is shown in the figure. Suppose that the low-frequency clock source is 32 kHz. When the timeout period setting bits are set to 011111, the timeout period is equal to 32 microseconds. I²C Interface Operating Principle. How does the HT8 MCU communicates with external devices through the I²C interface? Data is transmitted and received through a shift register. With the Data Storage Register SIMD, the MCU implements data transmission and reception. The Transmit and Receive Control Unit detects whether data transmission is completed or not. If yes, the HCF flag is set high and an interrupt is generated. The control unit also detects the start and stop signals on the bus. When a start signal is detected, the HBB flag is set high. When a stop signal is detected, this flag is cleared. The address register SIMA is used to store the slave address. The received data will be compared with the preset value of the SIMA register. If the addresses match, the HAS flag is set high and an address match interrupt is generated. At the same time, this received data also determines what mode the slave is in, which is reflected by the SRW flag, and then controls the slave operating mode through the HTX flag. In order to prevent false triggering of the start signal on the bus, the I²C two-line interface also includes a debounce circuit. In order to reduce the problem of I²C lockup due to reception of erroneous clock sources, a timeout function is provided. The timeout control unit is controlled by the SIMTOEN enable bit, the system low-speed clock, and the address matching flag. If the bus clock is not detected over the timeout period, an interrupt will be generated, and the I²C interface registers will be reset. SIM-independent interrupt. As the serial interface module of the HT66F3195 has integrated the SPI and I²C interfaces, this means that serial interface module interrupt, or known as SIM-independent interrupt, is triggered by the SPI or I²C interface. Each time the I²C interface transmission is completed, an interrupt request will be generated, then the SIMF interrupt request flag will also be set to 1. So what is the role of the SIM-independent interrupt? During data transmission, the CPU does not have to wait and can handle other tasks to speed up the operation. Here is a SIM-independent interrupt example. First, define the interrupt name. Then look up its interrupt address. An independent interrupt corresponds to a unique interrupt event. After the program enters the interrupt, the subroutine can handle the interrupt event. Application examples. As mentioned earlier, the I²C interface of the HT8 MCU can only be used in a slave mode, while the master mode requires a software emulation. Let's take a look at how to emulate the master mode. Based on what we have learned about the protocol, the master mode emulation requires to create several functions, including the start signal function, master detecting slave acknowledge function, I²C master transmitting 1 byte function, I²C master receiving 1 byte function, master acknowledge function, master not acknowledge function, and stop signal function. Now, let's look at the program example. The first step is to initialize relevant pins. Then write the start signal function, where the data line SDA changes from high to low during the clock line SCL high level. After transmitting the slave address, the master will detect whether an acknowledge signal is transmitted from the slave, which is implemented by a master detecting slave acknowledge function. First, set the SDA pin to input mode, then the master generates a clock signal that holds the SCL pin high for a period of time, then controls the SCL pin to output low. If the SDA is high during the SCL high level, the master will wait for a timeout period. If the SDA pin is not pulled low by the slave after the timeout period, which means there is no slave acknowledge signal, the master will pull low the SCL pin, set the SDA pin to output mode, then return the not acknowledge result. If the address is correct, the corresponding slave on the bus will pull low the SDA line during the SCL high level. The master will detect the SDA low level as an acknowledge signal, then set the SDA pin to output mode and return the acknowledge result. The next step is to write a master transmitting function, which not only transmits the slave address and the read-write bit, but also transmits data. First of all, the master controls the SDA pin to output mode. 1 byte has 8 bits, and the I²C data is transmitted with the highest bit first. Therefore, the master checks the highest bit of the data and controls the SDA pin to output the corresponding level, then the data shifts to the left, and the SCL outputs a clock signal by outputting high, holding for a period of time, then outputting low. During the SCL high level, the slave reads the SDA levels. The left shift is to move the next bit to be sent to the highest bit location. This operation will be performed 8 times until the master has sent 8 bits. Subsequently, the master controls the SDA pin to input mode to detect the slave acknowledge signal. This step is to introduce the master receiving function. First of all, the master controls the SDA pin to input mode, and 1 byte has 8 bits, which is used to determine whether the data reception is completed or not. If not, the master generates a clock signal that is to control the SCL pin to output a high level, keep high for a period of time, then output a low level. During the SCL high level period, the slave will output a data level through the SDA pin, and the master will read the SDA level at the same time, so that the master will receive a bit sent by the slave, and this operation needs to be performed 8 times until the complete 1 byte is received, indicating that the data reception is completed. Then the master controls the SDA pin to output mode and returns the received byte. Now let's go on to write the master acknowledge function and master not acknowledge function. When the master is the data receiver and the slave is the data transmitter, if the master needs to continue to receive the next data, it will generate an acknowledge signal to the slave, and the slave will continue to transmit data after receiving this acknowledge. If the master does not need to receive data, it can transmit a not acknowledge signal. The acknowledge function refers to that the master controls the data line SDA to remain low during the SCL high level period. The not acknowledge function refers to that the master controls the SDA line to remain high during the SCL high level period. The final step is to write the stop signal function that terminates the I²C communication. When the clock line SCL is high, the master controls the SDA line to change from low to high. The above has provided a complete example of I²C Interface Master Mode emulation. This is application example 2, which introduces how does an I²C master transmit data. The first step is to emulate the I²C master mode by software, which has been introduced in application example 1. Then initialize the pins, setting the SDA and SCL pins to input pull high mode to provide a high level for communication. Next, the master transmits a start signal. Then transmits the slave address and waits for the slave to acknowledge. If the slave does not acknowledge, the master transmits a stop signal to terminate the communication and returns the communication result. If the slave acknowledges, the master continues to transmit data. If the master does not receive an acknowledged signal after data transmission, or if the master has received enough data and transmits a not acknowledged signal to the slave, the master will then transmit a stop signal to terminate the communication and return the communication result. Considerations. In this section, we'll learn about what is I²C lockup. I²C lockup refers to a phenomenon when using the I²C communication protocol, in which 2 or more devices, such as master and slave devices, wait for each other during the communication process due to some reason, preventing them from communicating normally. Then what causes I²C lockup? During the normal communication process, one side accidentally resets while the other side is working normally. The communication state of the reset side is inconsistent with the other side, causing both sides to wait for each other, which results in a lockup. For example, after the slave transmits an acknowledged signal to the master by pulling low the SDA line, the master accidentally resets, and after the reset the master finds SCL high and SDA low, so assumes that the I²C bus is busy and will not operate on the bus. However, the slave waits for the master to pull low the SCL line. As a result, both sides are waiting for each other, which leads to abnormal data transmission and reception. How can we reduce the problem of lockup? When the SIM module of the HT8 MCU is used in the I²C mode, there is a timeout function to reduce the lockup problem caused by the I²C receiving erroneous clock signals. For example, a timeout counter starts counting on a start signal and address match condition, and is cleared by a clock falling edge. After an address match occurs, the slave starts timing, and under normal situations, the master transmits and receives data along with the clock signal, and the slave clears the timeout counter on the falling edge of the clock signal until the end of communication. If the master resets for some reason when transmitting the clock signal will be kept high or low and the timeout counter cannot be cleared, which causes the slave to think that the bus has been busy, and the subsequent slave data transmission and reception are abnormal, resulting in a lockup problem. When the timeout counter overflows, the I²C internal circuitry is reset, and the associated registers are also reset. For the slave device, in addition to using the timeout detection function of the SIM module, the watchdog timer can also be used to unlock the phenomenon. For the emulated master, it can actively transmit a stop signal to the I²C bus and then reinitiate communication to solve the problem. Course summary. In this course, we have learned the HT8 MCU's I²C interface, I²C communication process, I²C relevant registers, and how to emulate an I²C master by software. Through this course, you will have a clear understanding of the I²C interface. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.